Hello everyone, my name is Simon, and in this video we'll explore how to make a black hole in a real-time environment. Specifically, I'll be using Unity, but you could probably do this in any game engine. The exact implementation would probably be a little different, but the overall idea should be transferable to any environment. The plan for this video is to split it up in 3 parts. In the first part, we'll go over the mathematics, introduce the basic concepts of general relativity, and calculate the orbits of light rays. Then in the second part, we'll hop into Unity and go over how I implemented it. There are probably multiple ways to do it, but I'll just show what I came up with. So if you don't care about the mathematical details or you don't have the mathematical background to follow along, you can just skip to the second part. Finally, in the third part, we'll analyze the result and discuss which approximations could be improved. Okay, let's get started with the math. Classically, the path of a particle or an object is described as a vector function of time. From relativity, however, we know that time is dependent on the frame of reference. In relativistic physics, we use 4 vectors, combining space and time to spacetime. For 4 vectors, we typically use this notation, with the Greek letter index at the top. Sometimes, when there's no ambiguity, you can leave out the index and use bold characters. I will consistently use bold blue characters for 4 vectors, but I'll leave out the upper index from time to time to try to limit the amount of clutter in the equations. Because time is now a coordinate itself, it makes more sense to describe a particle's path in spacetime, often referred to as a world line, as 4 functions of a parameter, or in short, a 4-vector function of a parameter that we call sigma here. Sigma can be any parameter, but a natural one to choose is proper time, typically denoted as tau. This is the time that would be measured by a clock carried along the world line. Mathematically, proper time is defined as time multiplied by this factor, which is a decreasing function of the speed. If you're familiar with relativity, you'll recognize this immediately as the inverse of the relativistic gamma factor. For a non-constant speed, this should be written in the differential way like this. We have defined the position in 4-dimensional spacetime x alpha. We can also define the 4 velocity u alpha as a derivative of the position with respect to the proper time. For the time component, for example, this would be the derivative of the time component of x alpha with respect to tau, which turns out to be c gamma. The x component of the 4 velocity turns out to be gamma times the x component of the 3D velocity. The y and z components are similar. Finally, we can define a dot product for 4 vectors. It is similar to the dot product of 3D vectors, however the sign of the term with the time components is negative. It can be written in a neat way like this, where eta alpha beta is this 4x4 matrix. In the context of relativity, it is called a metric. This notation is called the summation convention, where repeated upper and lower indices are meant to be summed over, so like this, but without writing the summation signs. I will consistently write matrices as orange symbols with 2 lower integers. You might know that the dot product of a vector with itself is its length squared. However, for 4 vectors of spacetime, be wary that the length of a 4 vector does not behave the way that you might be used to. Spacetime is not Euclidean, which is immediately clear from the fact that the length of a 4 vector is not the sum of the squares of its components. Specifically for this context, it is important to note that 4 vectors with 0 length do not necessarily have to have all components equal to 0. Rather, the length of the spatial part must be equal to that of the temporal component. Let's now talk about light rays. Light rays, or photons depending on what you feel like at the moment, are massless, and thus travel at the speed of light. If you look at the definition of proper time, we see that it is 0. This means that anything traveling at the speed of light does not experience time, which is interesting on its own. However, for us, this means that proper time is not a good parameter to label points on a light-like world line. So let's take a different parameter, lambda. We can again take the tangent vector, using the parameter lambda as tau was used for massive particles or objects. For example, let's say a light ray is traveling in the x direction. Its path can be written as x equals ct, or parametrically as x alpha equals 1100 times lambda. If you look at the length of u, we see that it is 0. And this is a general fact for all light-like world lines. Along a light-like world line, the length of the tangent 4 vector is 0. For this reason, they are called null world lines. Now we'll introduce general relativity. In special relativity, what we discussed so far, spacetime was flat, and we used the metric eta. In general relativity, spacetime is curved. Mathematically, the curvature of spacetime is described by the metric. For a curved spacetime, we use the symbol g alpha beta instead of eta. Finding the metric for a certain physical system is very difficult. Luckily for us, this has been done long ago for those systems that are of interest to us. Specifically, we'll be using the Schwarzschild metric, which describes the curvature of empty space outside a spherical object. The metric looks like this in spherical coordinates, which is what we'll be using as well. M is the mass of the source of gravity. Often in general relativity, we use something called geometrized units, where the gravitational constant g and the speed of light c are 1 to clean up the clutter in the equations. In geometrized units, the Schwarzschild metric looks like this. It is time to investigate light ray orbits, but before we dig into the equations, it is helpful to search for symmetries in the system, because these indicate conserved quantities of motion. First, notice that the metric is independent of t and phi. Therefore, these two quantities are conserved along the path of freely falling objects or light rays. In a flat spacetime, these would correspond to the time and phi components of the 4 velocity. The vector 1, 0, 0, 0 is typically named xi, and the vector 0, 0, 0, 1 is typically named eta. This is a bit of an unfortunate naming convention, as it might lead to confusion with the metric eta. Nonetheless, the metric eta is a matrix, so I will always color it orange, whereas the vector eta will be blue. Writing these out for the Schwarzschild geometry, xi.u is some factor times dt d lambda, and eta.u is some factor times d phi d lambda. These conserved quantities will be very important, so let's give them a name. Xi.u is called -e by convention. This way, E corresponds to energy per unit rest mass in a flat spacetime. So, by a lack of better intuition, we'll call it energy per unit rest mass everywhere. Eta.u is conventionally called L, such that L corresponds to angular momentum per unit rest mass in a flat spacetime. And again, we'll call it that everywhere. Secondly, since the metric is spherically symmetric, you can always orient the spherical coordinate system such that the light ray orbit lies in the equatorial plane theta equals pi over 2. It is finally time to calculate the deflection of light by a black hole or any other spherically symmetric object. We start by writing out the null worldline condition of u.u equals 0. We chose theta to be pi over 2, in which case the entire orbit is in the equatorial plane. Thus d theta d lambda is 0. Using the definition of E, we can replace dt d lambda, and using the definition of L, we can replace d phi d lambda. That leaves us with this equation, where only dr d lambda is left. After some more manipulation, we can write it like this. Technically there's also the negative root, but this is the same orbit just in the opposite direction, so we can ignore it. Using the definition of L again, we can find an expression for dr d phi, or inversely d phi dr. It is helpful to look at a schematic of our problem now. So we have our orbit in polar coordinates r and phi. Delta phi is a total angle swept out as the light ray proceeds from infinity and back out again. The angle we are looking for is this delta phi minus pi. R1 indicates the turning point, which is where the light is closest to the source of gravity. Also, R1 is the halfway point of the orbit. Finally, the shape of the orbit is determined by the impact parameter b. In our case, this can be proven to be the absolute value of L over E. I won't prove it here because this video is already going to be more than long enough, but for those who do want to give it a try, the key is to take the limit of r going to infinity of this absolute value of L over E, and prove it is the impact parameter like we drew here. Coming back to our expression for d theta dr, we can replace this E squared over L squared with 1 over B squared. The total angle swept out delta phi is twice the angle swept out from the turning point r1 to infinity, which gets us this integral. r1 is a value of r for which everything in the bracket vanishes. We can make this integral more insightful using a change in variable. Introducing the variable w equal to b over r, the integral can be written like this, where now w1 is the value of w for which everything in these brackets vanishes. In this form, it becomes clear that the shape of the orbit is entirely determined by the ratio of b and m. Finally, the deflection angle is this delta phi minus pi. This integral can be calculated numerically for different values of b over m, the result of which is a graph that looks like this. It's a steeply declining function of the impact parameter, which makes sense as far away from any gravity source we expect no bending of light. We can also see that the deflection angle shoots up to infinity for some finite value of b over m. To be precise, the deflection angle becomes infinite for a value of b over m of the square root of 27. The physical interpretation of this is that at a certain distance from the center of gravity, light orbits in a circular path. Slightly closer to the center of gravity, light will spiral inwards, while slightly further away, light will spiral outwards. This distance can be calculated to be 3m, but I won't do it here. There's one thing left to do. We will want to calculate E, and currently it is a function of the time component of u. However, it would be more useful to express this as a function of the spatial components of u, because then we can calculate both E and L from a given position and direction of the light ray. To do this, we start again with the condition u.u equals 0. We again write it out for the Schwarzschild geometry. After rearranging terms, multiplying both sides with 1 minus 2m over r, cleaning up, and taking the square root, we find this expression for E. At this point we're done with the math. However, since we want to make a real-time black hole, we cannot do a numerical integration every time we need to know how much a light ray bends. After playing around with some functions, I found a decent approximation for the deflection angle. This is what I came up with. It's by no means pretty, but it does approximate the deflection angle well enough for practical purposes. It deviates slightly close to the asymptote, but for me it was good enough to move on. Only the first term has any physical meaning, as it is the first term of the Taylor expansion of the function for the deflection angle. Other than that, all terms are utterly meaningless. You can definitely do this properly or play around with functions more to get a better approximation, but honestly, I don't think it would be noticeable in any practical application. Besides, as we'll discuss at the end of the video, the other approximations we're making are much more significant. We're now in Unity. I'm using the universal render pipeline, but you can use whatever you like. The scene consists of a camera, a global volume which handles the post-processing, a reflection probe, and a large plane that is a black hole. I've scaled it up by a factor of 100 here, so this is very big. The skybox is an HDRI environment made by Barton. He has made a ton of mind-blowing space environments. I'll link his ArtStation in the description, definitely go check him out, he does amazing work. This one specifically is from his Rubellite collection. The plane has a script called face camera, which makes it face the camera at all times. As you can see, it's a very basic script. On the main camera there are two scripts. The first one is called camera controller, which lets you control the camera with WASD EQ, together with the player input component. This is a script. I won't go over it in detail because this is not a tutorial on how to do input and movement controllers. Secondly, there is the track script, which is similar to the face camera script and will keep the camera pointed towards the black hole. Let's take a closer look at the shader now. This is an unlit shader, meaning that the shader only has a color and does not interact with light. So the color of the shader is precisely the color that gets drawn on the pixels. It might look complicated at first, but you'll see that it is relatively straightforward once you know the math. We start by getting the view vector. We then decompose it into the R and phi components. This normal vector is the vector pointing from the black hole to the camera, because the plane is always oriented to face the camera straight on. We then project the view vector along this R direction to get the R component. Subtracting the R component from the original view vector, we're left with the part of it that is perpendicular to the R component, which is the phi component. Then we take the length of both of these, because that is all we need to know to calculate B. We also calculate the distance between the camera and the black hole. All of this is used to calculate B. This is a subgraph that looks like this. It's just calculating L and E using the expressions we derived earlier, and then taking the absolute value of L over E. We then calculate the deflection angle from B. This is another subgraph. I could have combined this one with the calculation of B in one subgraph, but I like to keep them separate because I like to think of them as two different steps in the process. Anyway, looking in this subgraph, we start by dividing B by M. All of this is the ugly approximation function that I came up with. Over here we check if B over M is greater than the square root of 27. In other words, if the light ray escapes to infinity, this returns true. If the light ray falls into the black hole, this returns false. This value here is actually ever so slightly larger than the square root of 27 to stay away from infinite values. This Boolean value is then used in two places. First, we make the deflection angle 0 if the light ray falls into the black hole. This probably isn't necessary, but again, this way we stay away from infinite values. Secondly, we want to output a mask of where the black hole is. This is done by switching between 1 and 0 depending on the Boolean value. So this mask is white outside of the black hole and black inside of the black hole. Then we use the calculated deflection angle to rotate the view vector. For this, we use this node, which rotates a vector around the given axis. However, now we need an axis to rotate around. Here I need some basic vector math. Let's say the camera is here, and we have a ray going in this direction. The vector pointing from the black hole to the camera is this one. Taking the cross product returns a vector that is perpendicular to both of these vectors, and this vector we can use as the axis to rotate the ray direction around. Coming back to the shader graph, this normal vector is again the vector from the black hole to the camera. Then we take the cross product with the view vector to get the axis around which to rotate. Now all that is left to do is to access the reflection probe. However, as the name might suggest, the reflection probe is meant to be used for reflections. Therefore, this node takes in the view vector and a normal vector, and internally reflects the view vector along this normal before returning a color value. We'll need to undo this reflection, or rather, we need to pass in a vector such that after reflecting it across the normal, this is pointing in the intended direction. To do this, we start by decomposing the rotated view vector into the R and phi components again. The reason for doing this is that we can now invert either the normal component or the tangent one, or both. I had a gut feeling that one of these options would give the result we're looking for. And indeed, after some trial and error, I found that just inverting the normal component does the trick. Finally, we make everything inside the black hole black. We do this by multiplying the entire image by the black hole mask. And that's it, we now have a black hole. If we hit play, we can see the black hole in the distance. We can move with WASD. We can move up and down using Q and E. It looks great, and it's surprisingly fun to play around with. You can, for example, switch out the environment for a different one, and just flying around and seeing how the light is deformed is very satisfying. Let's take a closer look at the results. There are 3 different regions in the image. The first region is far away from the black hole, where light gets only slightly bent. The second region is close to the black hole, where lights get bent strongly. You can see that apart from the deformation, the image in this region is flipped as well. Looking at the light paths in this region, you can see why. They cross behind the black hole. The boundary between the first and the second region is called the Einstein ring. This is where all light rays from exactly behind the black hole are bent into the camera. If you think about it in the opposite direction, where light rays are emitted from the camera into different directions, which by the way is what is actually done in render engines, the Einstein ring is where the rays are bent in such a way that they all go in the direction the camera is facing after passing the black hole. Finally, the third region is a black part. This is not the event horizon, however. The boundary of this region is where light rays enter a circular orbit and thus never reach the camera. As I mentioned previously, this is at a radius of 3m, while the event horizon is at a radius of 2m. Light from a source in between radius 2m and 3m can still escape in some directions. However, in our situation, all light is coming from far away. In this case, light rays that get closer than 3m from the black hole will always spiral inwards. The last thing I want to talk about is the approximations we have made here. Obviously, we approximated the deflection angle by some ugly function I came up with, but that is not the most influential one. One approximation I haven't yet talked about is the fact that the camera is not infinitely far away. This means that the deflection angle we calculated is an overestimate of the actual angle that a light ray is bent. This approximation is not at all accurate when the camera is close to the black hole. So if there is an approximation you would want to improve, it's this one. My idea for solving this is making an image texture that contains the deflection angle as a function of b and the distance of the camera to the black hole. And then instead of calculating the deflection angle within the shader, we would just read it off the texture. Another approximation I didn't mention very explicitly is that all light is coming from infinitely far away, which is not the case for typical in-game environments. However, in an astronomical context, this is not a bad approximation at all. One thing to note is that this specific implementation will only work when the only environment is a skybox. If you have a 3D scene, you will have to do more work. For example, you could try to use a camera texture outside of the Einstein ring and the reflection probe inside of the Einstein ring, but it does complicate things quite a bit. That's going to be it for me today. Thank you for watching. If you have any questions or remarks, please let me know in the comments. If you followed along, I'd love to see what you can come up with to make the result look even better, and I hope to see you whenever I decide to make another video.